A quote from Professor Carlos Frank, Durham University. "I've spent my whole life developing a particular theory of the universe, and now that theory is being challenged. I welcome that because that's how we move forward. That's how we make progress in science." James Webb is overturning pretty much everything in cosmology that has been held as truth for 100 years. A new ultra-deep image shows again that we have made mistakes in astronomy. The telescope that was supposed to show us the first stars of the universe is becoming a killer of the previous worldview and may bring us a whole new science. Not all researchers are shivering in fear at the new facts. Many scientists welcome the developments because it has long been clear that something was wrong with our old theories. The discrepancies in the measurement of the expansion rate of the universe alone should have shaken researchers awake years ago. But instead of interpreting the warnings correctly, they clung to old theories. The cosmic microwave background radiation, or CMB for short, is considered to be the oldest light in the universe. The CMB was created around 380,000 years after the Big Bang, when the universe had cooled down enough for electrons and protons to form stable hydrogen atoms. Researchers call this transition reionization, and this change made the universe permeable to light. The CMB was first discovered in 1964 by the American physicists Arno Penzias and Robert Wilson. While the two scientists were working on a new type of antenna technology, they came across a constant noise coming from every direction in the sky. This discovery was long regarded as one of the strongest pieces of evidence for the Big Bang theory. Penzias and Wilson shared a Nobel Prize and went down in the history of astrophysics. The CMB very probably offers a snapshot of the young universe. Tiny temperature fluctuations are important sources of information about the conditions in the universe shortly after the Big Bang. Scientists use the CMB as a reliable imprint of the basic metrics of the material cosmos to measure the expansion rate of the universe, among other things. The astronomer Edwin Hubble had already made this calculation in the late 1920s. Hubble had discovered that distant galaxies move away from us in all directions and that their speed is proportional to their distance. Today, we know these observations as the Hubble law or the Hubble constant. Of course, Hubble did not yet have such good measuring techniques as were used decades later. When the CMB was discovered, researchers recalculated the rate, and the new value was significantly lower than the figure Hubble came up with. Later, scientists recalculated the rate again. With Type 1a supernovae as standard candles, astronomers had such stable light available that this light could be used as a kind of reliable measuring point. The distance is calculated with standard candles by comparing the observed brightness with their actual luminosity. The measurements within the CMB yielded an expansion rate of about 67 kilometers per second per megaparsec, while the measurements using the supernovae yielded about 74 kilometers per second per megaparsec. What does S8 really tell us? Did you know that this difference in determining the expansion rate of the universe has been known since the 1990s? Since then, researchers have known, or rather suspected, that something could be wrong with the assessment of the CMB, the measurement methods, or the idea of the expansion of the universe. The discrepancy between the various measured values of the expansion rate of the universe is known in science as the S8 tension or Hubble tension. The implications of this tension are not just any difference in measurement. The different results show us that profound things about how we have understood the universe so far are flawed. For a long time, researchers were at a loss. Since the James Webb Space Telescope went into service, the telescope has given scientists some surprises that may now shed light on the problem of the expansion rate of the universe. Galaxies so old and so mature that their formation must theoretically predate the Big Bang are completely overturning the old science. In astrophysics, there is no longer talk of discrepancies or differences in measurement. Researchers are talking about the biggest crisis in modern astronomy. Not only could the rate of expansion of the universe be wrong, the whole idea of expansion or the Big Bang is being put to the test. We see in Webb's images evidence of a universe that is very different from what we have long thought. The S8 tension was a first warning, and all researchers who still believed in the old theories now have a problem. Do we really know nothing about the universe? These days, many scientists are standing on the shambles of their life's work. They look into space in horror and no longer understand what they are seeing. In view of the crisis in science, we have to ask ourselves, what do we really know about the universe? To answer this question, we need to understand how science works. Theoretical scientists use a complex web of mathematical models, empirical data, and deductive reasoning to draw conclusions from the general to the specific. Their quote-unquote knowledge comes from a combination of observed phenomena, experimental results, and many theoretical analyses. The word theory alone shows us that these are constructs and ideas, but not truths. The only practical knowledge we have are the images that telescopes provide us with. The sounds, waves, and radiation that we can capture with radio telescopes, and the latest data that neutrino measuring systems or gravitational wave detectors bring us. With the James Webb Space Telescope, we now have an instrument at our disposal with which we can for the first time break down the oldest light into individual frequencies and analyze it in a way that has never been possible before. Webb can show us which elements were predominant in galaxies over 13 billion years ago, how much mass was contained, and how many stars this indicates. And the telescope can reconstruct the shape and direction of movement of a galaxy. But Webb can also have weaknesses. In some images, for example, the telescope cannot determine with certainty whether we are really seeing galaxies or black holes that shine just as brightly as a galaxy due to huge accretion disks. We have to face the fact that our science has long developed in a way that has accepted too many eventualities as truths and has long disregarded alternative explanations. Research has long been certain that it is right. The latest findings from the James Webb Telescope are important clues to replace theories with new truths, as has happened dozens of times in science. Scientists are currently waiting. The new discoveries are too crazy, and it seems impossible for many researchers to come up with new explanations right now. The new findings are shaking the foundations of our physics, and that scares many researchers. The teachings of physics today are still largely based on Isaac Newton's teachings, who conducted research in the 17th century. For centuries, his laws of motion and gravity were the foundation of physical understanding of the real world, including the universe. Newton's laws explain the movements of objects under everyday conditions and work quite well on Earth. In space, however, his ideas had to be extended, and this was largely done by Albert Einstein at the beginning of the 20th century. His special theory of relativity was published in 1905 and revolutionized the understanding of space and time. Einstein proved that space and time are relative to each other and depend on the movement of the observer. The general theory of relativity followed in 1915 and extended the concept with mathematical proofs of gravitational phenomena based on the curvature of space-time by masses such as stars or galaxies. Einstein's laws and ideas were coherent in many areas, but he also reached his limits. The researcher knew during his lifetime that his theories would never be sufficient to describe the universe as a whole. He dreamed of finding the world formula, but he did not succeed. Incidentally, no other researcher has succeeded to this day. Where is the mistake? Wouldn't it be interesting to know where the mistake lies? Michio Kaku, the popular astroscientist from the USA, said in an interview that the person who solves this problem is sure to win a Nobel Prize. Let's see what facts scientists may have overlooked. Where have they possibly misinterpreted phenomena? Or are our telescopes to blame? At the top of the list of suspects for the real causes of the cosmological crisis are dark matter and dark energy. Our current models of the universe include concepts that dark matter and dark energy together make up about 95% of the universe. However, neither has ever been directly observed, and consequently, their real existence has never been proven. Either they do not exist at all, and we have to explain the expansion of the universe and the dynamics in galaxies differently, or perhaps both have properties that we do not yet know of. One idea currently under discussion is that the physical properties of the two dark components have changed over time, which could even mean that we are dealing with some kind of intelligence. The next thing to be put to the test is gravity. This force, which supposedly leads to attraction through mass or curvature in space-time through mass, has not yet been proven. The ideas of space-time curvature originate largely from Einstein and have been proven true many times over. However, we cannot currently rule out the possibility that gravity has completely different properties than we thought, or that it's a different effect that causes the gravitational pull on and between objects. Over the decades, a number of values have been established in our cosmology and astrophysics as so-called cosmic constants. These are values that are largely reliable because they hardly change. Calculations have shown that small variations of these alleged constants bring new momentum into the universe and that we could explain a number of phenomena without the existence of dark energy. It is also possible that our interpretations of the redshift of light are wrong and that for decades we have measured incorrect distances within the cosmos and also incorrectly determined the age of galaxies. Perhaps our assumptions about the initial conditions of the universe were also incorrect. We may have misinterpreted the cosmic microwave background radiation, and it's also possible that the universe cannot be traced back to a single starting point. This would mean that the idea of the Big Bang is wrong. Although we are technologically advanced, we cannot rule out minor errors in the Webb telescope or other observational instruments. What is the problem? Can you imagine that big names in physics like Stephen Hawking or the father of dark matter, Jan Oort, and many other astronomers based their theories on an illusion? It sounds crazy, but it's a fact that from around the 1930s, researchers based our cosmology on the existence of dark matter. However, it has not yet been proven that this dark matter really exists. In order to simulate the formation and evolution of galaxy clusters and virtual galaxies, we had to include at least one element of which we have virtually no idea whether it is real. Here's the catch. For a while, the calculations still worked. Dark energy and dark matter were like physical stopgaps that served their purpose, but then the models reached their limits. The Hubble tension, which we will discuss later, was actually the first warning sign. Over time, more and more inconsistencies were added to the currently valid cosmology, and now, James Webb and Flamingo are finally destroying the old dreams of scientists to have understood and decoded the universe. Somewhere, we have overlooked something crucial. A key feature of Flamingo's work is that this study not only works with models of dark matter, but also gives space to the world of ordinary matter and new particles such as neutrinos. Ordinary matter makes up about 16% of all matter in the universe, and understanding it is crucial if we really want to understand cosmic evolution. New simulations have been and are currently being run on powerful supercomputers with varying scenarios and taking into account new factors such as galactic winds and the mass of neutrinos. In this way, scientists have been able to significantly improve the accuracy of predictions. But the real breakthrough to a universal understanding of cosmology has not yet been achieved despite this dedicated work. The generated simulations and countless virtual data are like an exciting puzzle, and every new real observation from James Webb or other telescopes around the world is valuable fodder for ever new simulations and the development of new data analysis techniques. Cosmological dilemma is perfect. Would you ever have believed that a telescope could drive scientists to the brink of madness? Never before have we heard so many astronomers and cosmologists say things like, "We don't know anymore," "We're at a loss," or "Nobody knows what's coming next." Some are in a spirit of optimism and others are depressed. What they have believed in for decades is suddenly no longer true, and some scientists are having to start from scratch these days. Those who believed in the Big Bang 13.8 billion years ago and a subsequent dark era of the universe are confronted with bright and very advanced galaxies that actually existed when the universe was just beginning to produce its first stars. James Webb discovered a number of galaxies that already shone like ancient galaxies in space just 300 or 400 million years after the Big Bang. This sheds a completely new light on the big question in physics. How much matter actually exists? How was it formed? And above all, when? Flamingo exacerbates the dilemma by depicting, in particular, the large-scale cosmological structures and showing here too that the real distribution of matter in the universe does not match the old calculations. Flamingo's fascinating images virtually show the distribution and evolution of all known galaxies and galaxy clusters in space. We now know that matter and galaxies move along a cosmic network. This network is one of the largest currently known structures in the universe and consists of filaments that are probably made up of a mixture of normal matter and hypothetical dark matter. The ideas of dark matter have so far served as an explanation for many effects of gravity and other forces acting between galaxies and even larger structures in the universe. Since James Webb and the discrepancies in the simulations have shown that the calculations do not work out in the upper structures, conventional matter and alternative theories have come back into focus. There are theories according to which slight variations of supposedly fixed cosmic constants can explain almost all visible effects of cosmology and galaxy movements, even without assuming the existence of dark matter. The Mond theory, for example, modifies Newton's laws of motion at very low accelerations as they occur in the outer regions of galaxies and can thus explain the observed rotation curves of galaxies even without the assumption of invisible matter. This, of course, raises questions as to whether all our calculations and ideas regarding the dominance of dark matter in the universe have been wrong so far. The Great Discrepancies in Cosmology, Hubble and S8. The astronomer Hubble is considered one of the fathers of the Big Bang theory. In the 1920s, he observed the movements of galaxies and came to the conclusion that distant galaxies were moving away from us. This gave birth to the idea of expansion, for which there was later further evidence, for example, in the cosmic background radiation. The universe was later measured on the basis of these values, and these values again played a decisive role in determining the age. But here too comes the catch, because improved measurement methods and the constant progress of our technological possibilities made new measurements possible. And lo and behold, small but telltale discrepancies emerged, which are now known as the Hubble tension. Basically, it says that direct observations of nearby stars and galaxies show a faster expansion than the calculations based on the light of the Big Bang. Flamingo has now discovered a new discrepancy, this time within the so-called S8 parameter. This parameter deals with the distribution of matter in the universe and represents how clumped or clustered the matter is regionally in the universe. These observations must somehow be compatible with the cosmic background radiation. The radiation, called CMB for short, is considered a relic of the Big Bang and a kind of imprint of the structures that were present in the young universe. What we see today can be traced back directly to these first structures. It's a bit like blowing up a balloon with a dot on it. The bigger the balloon gets, the more the dot changes until it's possibly no longer recognizable as such. But if we let the air out, the stretched structures reunite to form a dot. The S8 values basically describe the expansion of the balloon, or rather how the matter behaves on this expansion. Since the CMB is supposed to be something like the primordial matrix, the current measurements must be able to be calculated back to this matrix. However, this is not always possible, and this is where another problem begins. The CMB experiments suddenly yielded shifted higher S8 values, and it's therefore clear that we also have a discrepancy here, which further exacerbates the crisis. There is, of course, a connection between the S8 voltage and the Hubble voltage. Taking again our example of the balloon, the expansion rate S8 stresses would show discrepancies in the distribution of patterns on the balloon, and the Hubble stress occurs at the speed and regularity corresponding to the expansion of the balloon. Scientists are faced with a puzzle, and no one now knows what exactly this will mean for the future. These sources of error have already been found. Can you imagine how feverishly scientists are currently searching for the answers? The researchers who crack this cosmic puzzle are not only rewarded with recognition, awards, and new research funding, they are also driven by a curiosity that keeps them searching. New aspects are currently being included in the calculations in order to find a way out of the dilemma. Where were the errors? Which force or which type of matter have we not sufficiently taken into account so far? Or are there possibly completely new factors in the universe that we can now discover? It's hard to imagine the complexity scientists have to deal with when trying to calculate the dynamics of the universe. We know how difficult it can sometimes be to predict the weather on Earth and to reconstruct the complex processes in the atmosphere. In the universe, these calculations and predictions span incredibly large dimensions, both temporally and spatially, and within this time and space, there are many components and lots of unknowns. In addition to the prime suspect, dark matter, many other values are currently under scrutiny, and others are suddenly receiving more attention because their role may have been underestimated in the past. Ordinary matter, for example, is not only subject to gravity, but also to parameters such as the pressure of gases, the influence of galactic winds, supernova explosions, or the activities of enormous black holes. We do not yet know what role neutrinos and other extremely charged particles that are shot through space by these events play. Our universe is probably a complex interplay, similar to the ecological dynamics on our planet. Imagine if scientists wanted to describe the processes, interrelationships, and forces at work in a chaotic flower meadow, or use computer simulations to depict the processes in this habitat. It seems as if there is only one topic in the astronomical world at the moment, and that is the deployment of the revolutionary James Webb Space Telescope. However, in view of the countless insights that the complex instrument is expected to deliver in the near future, we must not forget one thing. The mission of Webb's scientific predecessor, Hubble, is also still in full swing. However, the more than 30 years that Hubble has now spent in space have left clear traces. Launched on April 24, 1990, the instruments of the 11.6-ton telescope sometimes show clear signs of wear. Accordingly, the failure of some components has already caused switching to backup systems. Despite this, Hubble will continue its research service for at least 4 more years. When the day finally comes that operations can no longer be maintained, the Space Telescope will be able to look back on an unprecedented success story. Planning the future. Good things take time. As early as 1946, Lyman Spitzer presented the first concept for a scientific telescope in Earth orbit. However, before the astrophysicist was engaged to design a large space telescope, another 2 decades were to pass. To bring these revolutionary plans to reality, the leaders of the National Academy of Sciences turned to NASA. Several feasibility studies and 4 orbiting astronomical observatory satellites later, the plans for Hubble's elaboration took concrete shape. However, in view of the costs of up to $500 million, the Budget Committee of the U.S. House of Representatives immediately rejected the idea. So, from then on, the task was to find ways to push down the price and make it possible to finance the groundbreaking project. ESRO was brought on board to fund the solar cells. In return, ESA's predecessor was given observation time and a scientific say. The main seal was also to be reduced from the original 9 feet to 7, so the new price tag of $200 million was finally blessed by Congress. Originally, the telescope named after Edwin Hubble, the discoverer of the expansion of the cosmos, was to set out on its research mission as early as 1983. However, internal problems and the terrible Challenger accident meant that the launch date had to be postponed by another 7 years. But still, the ambitious undertaking did not experience good fortune. An unexpected main mirror error led to the fact that the first Hubble photographs were practically useless. It would take 3 more years before the problem could be solved with the help of the CoStar mirror system. Astronomical success story. Given the decades of planning and the major complications that preceded Hubble's launch, one wonders why experts were so eager to place a technical research eye in Earth orbit. In fact, this choice of location has some significant advantages over Earth-based instruments. Space telescopes are not confronted with the filtering effect of the Earth's atmosphere. This unpleasant effect would otherwise affect certain wavelengths in the electromagnetic spectrum, and also disturbing air movements can be avoided in this way from the outset. Before the technical device the size of a minibus left our blue home planet, it was given truly ambitious mission objectives. Just like Webb today, Hubble was to raise knowledge of the cosmos to a completely new level. With a resolution never before achieved, the instrument was to take a closer look at stars, planets, nebulae, black holes, and galaxies than ever before. A look at all the milestones Hubble achieved in the past 3 decades shows that it lived up to scientists' hopes brilliantly. Thanks to the study of the Cepheids, a group of stars whose brightness variations are strictly periodic, the cosmic distance scale has been recalibrated. In turn, the observation of distant supernovae should deepen our knowledge of the accelerated expansion of the universe. Moreover, thanks to Hubble, we know that a supermassive black hole lies dormant in nearly every galactic center, where it exerts a significant influence on the overall galactic evolution. Countless exoplanets were also tracked down and added to stellar maps as part of the mission. View into the depth. In addition, however, to the milestones just described, Hubble is also known for its legendary deep fields. According to the report, these complex images gave us an unprecedented glimpse into the gigantic depths of space. The first deep field was to be taken in December 1995, composed of 342 individual images. The Hubble Deep Field literally shows us the immense diversity of the universe. According to this impressive image, we can see more than 3,000 individual galaxies. Some of these gravitationally bound collections of stars lying some 12 billion light-years away from us. In addition, we can see some bluish shimmering structures on this comparatively small section of the firmament. Although the individual structures have not been precisely categorized, it is reasonable to conclude that we are dealing with large cradles of stars, distant quasars, and possibly ancient white dwarfs. While the image leaves us in awe with all its sparkling objects, it was also of unparalleled value to the scientific community. Accordingly, the first deep field was able to detect a large number of galaxies with strong redshifts. This effect is again due to the constant expansion of the cosmos. As the expansion increases, so does the distance that gapes between us and these remote galaxies. In the same breath, the wavelength of the light of the star collections increases, the further they drift away from our home planet. In view of the positive echo, which the first Hubble Deep Field triggered both in the technical and in the media world, it's not surprising that Hubble let its technical view wander again into such remote areas shortly after the turn of the millennium. The so-called Hubble Ultra Deep Field, which was taken between September 2003 and January 2004, held the title of the deepest image of the cosmos for 8 years. In view of the 10,000 galaxies and structures that shine towards us in this image, however, we should not forget that the section captured on image covers just 1/40,000,000th of the entire starry sky. If Hubble wanted to capture the entire firmament in such a resolution, it would take 1,000,000 years. And this time too, the cosmic view into the depths turns out to be a scientific milestone. Accordingly, on the ultra-deep field, which is composed of 800 individual images, we see some of the faintest galaxies discovered to date. The light of some galaxies took a whopping 13 billion years before it reached our terrestrial eyes. In other words, this means that we see the corresponding collections of stars as they appeared just 800 million years after the Big Bang. However, even this glimpse into the cosmic depths was still not extreme enough for the experts. This changed only on September 25th, 2012, when the Hubble Extreme Deep Field entered the scientific stage. Over a period of 50 days, 2,000 individual exposures were taken. In the end, this once again produced the deepest image of the cosmos ever. Some of the 5,500 galaxies that we can marvel at here show themselves as they were 450 million years after the birth of the cosmos. Hubble's legacy. Those who have already been awestruck by the Hubble Deep Fields we have just seen will be even more amazed when they recall that Webb is up to 100 times more sensitive to electromagnetic radiation than its scientific predecessor. As is well known, Hubble's air has recently given pictorial proof of its extraordinary performance. Webb's first deep field gives us an authentic foretaste of all the remote secrets of the cosmos that will be uncovered in the coming years of research. In detail, we recognize the galaxy cluster SMAC 0723 in the image unveiled on July 11, 2022, captured on image by the near-infrared camera NIRCam. This area in the constellation Flying Fish is located about 4.6 billion light-years from our blue home planet. If some structures on this image appear unusually distorted to you, you have just caught a vivid impression of the gravitational lensing effect. In detail, this is the deflection of light by large masses. Consequently, the light from a more distant source is affected by an apparent object in front of it, the gravitational lens. To see how much the astronomical future differs from the past, it's worth taking a look at the direct comparison, because in fact, the corresponding region was also photographed by Hubble. Although we also recognize countless radiating structures in this image, in terms of colorfulness and detail, however, the Hubble image cannot keep up with Webb's groundbreaking features. Not only can we see the individual structures on the Webb image much better and sharper, in fact, we also see some objects here that Hubble could not capture at all due to its technical limitations. In fact, the James Webb Space Telescope was designed specifically for infrared astronomy. This means that the $10 billion instrument is capable of working from the red part of the visible light to the mid-infrared spectrum. In this way, Webb is expected to provide us with a direct glimpse into those cosmic mysteries that are currently the great unknown. Hand on heart, in most people's daily lives, dimethyl sulfide, or DMS for short, probably plays no significant role. In fact, most people have probably never even heard of this particular chemical compound, even though they have very likely encountered it at one time or another. In detail, DMS is formed by microscopic algae, the phytoplankton, which drift in the uppermost layers of the ocean, and it's responsible for the typical smell that we notice when we are at the beach. Apart from its sniffing properties, DMS also has another important characteristic. So far, we only know of biological sources for this sulfur compound. And where the production of a substance requires the help of organisms, it's understandable that DMS plays a very special role in the search for extraterrestrial life. And even more understandable at the cries of joy that came from the lips of the Cambridge astronomers in September 2023. After all, the James Webb Telescope had detected nothing less than this potential biosignature on the exoplanet K2-18b. The overwhelmed discoverer Niku Madhusudan then told the press that he and his colleagues were completely shocked by their readings. No wonder, because after all, the existence of DMS in the vastness of space is nothing less than a serious indication of extraterrestrial life. And what initially came as a shock to the experts soon developed into almost euphoric reporting, which unceremoniously elevated the James Webb Telescope to the key to the cosmic search for life. But is the matter really as clear-cut as it seems? If the corresponding molecule on Earth is only produced by living things, and we then discover it on an alien body, why hasn't NASA officially announced that our microscopic neighbors are slumbering on K2-18b? Well, that's because, as so often, the devil is in the details. But basically, the conditions in the case of K2-18b are anything but bad. Is the water world a haven for life? Located about 120 light-years from us in the constellation Leo, the celestial body is under the exciting suspicion of being a Hycean planet. In other words, a planet whose surface is completely covered with water and can therefore support life. And while K2-18b was added to the star charts in 2015 with the help of the Kepler Space Telescope, it orbits its central star, the red dwarf K2-18, within the habitable zone. This, in turn, describes the distance range at which a planet must be located in relation to its host star for water to be able to exist there in a permanently liquid form. As we all know, the cool, wet element is considered one of the fundamental pillars for the development of life similar to that on Earth. And although K2-18 is significantly cooler than the Sun, its planetary companion receives roughly the same radiation as our Earth due to the given constellation. The bottom line is that K2-18b is only 0.14 astronomical units away from its parent star, so that it takes just 33 days for a complete orbit. And indeed, the Pro column on this life discussion list also contains the entries methane and carbon dioxide, and thus two further indicators that suggest that we may actually be dealing with a habitable planet here. If this is really the case, it would be a cosmic novelty because so far, these exotic water worlds only exist on paper. But while the detected large amounts of methane and carbon dioxide in combination with the lack of ammonia suggest that K2-18b is a Neptune-like planet covered by liquid water, the detected substances also present an unfortunate complication. They make it all the more difficult to interpret the DMS data correctly. The mystery of the biosignature. In principle, the DMS signal was anything but pronounced in the collected data sets, and it only revealed itself when the data was analyzed in a very specific way. The matter was not made any less complicated by the fact that the DMS signature identified by Webb's near-infrared spectrometer, NIRSPEC, appeared in a spectral line at a wavelength of 3.4 micrometers, and thus in the very range that overlapped with the methane. And that is precisely the crux of the matter, because the scientists believe that distinguishing between DMS and methane is simply beyond the capabilities of NIRSPEC. But does this also mean that Webb's capabilities have already been fully exhausted, and that we will not be able to uncover the true background to the DMS question? Well, fortunately not. The researchers also emphasize that unequivocal proof is possible in principle. After all, DMS and its breakdown products also generate a signature in the mid-infrared range between 9 and 13 micrometer wavelengths. And conveniently, this is exactly the range in which Webb's MIRI spectrometer works. While the first NASA announcement still spoke of a possible detection of the molecule dimethyl sulfide in this context, the Cambridge scientists finally wanted to know more. And so it happened that the astronomers once again used Webb's sharp infrared vision to get to the bottom of the mystery surrounding the supposed biosignature. In the course of this, the experts allowed 8 hours for the targeted search for DMS. 1 to 2 days later, the research team should then receive the data and begin with the evaluation. However, it's in the nature of things that such a data evaluation is, to say the least, laborious. Or in other words, it takes months before it's fully completed. The good news, however, is that the experts have already been working on the analysis for half a year, and that it can therefore not take much longer before the latest findings of the presence of DMS on K2-18b are published. When we can detect the DMS. Fortunately, the rest of the astronomical world is not condemned to just waiting and twiddling their thumbs in the meantime. After all, they can also approach the DMS question from a theoretical point of view. In other words, with the help of their models, scientists are able to check when we will be able to detect the existence of DMS on K2-18b. And that is exactly what the team, led by Shang-Min Tsai, of the University of California in Riverside has now done. In detail, the researchers reconstructed K2-18b and its possible biochemistry using several models, simulating the planet-covering ocean and atmosphere. The scientists then had to test how much DMS our extraterrestrial micro-neighbors would have to produce for it to accumulate in the atmosphere in a way that we could detect, and how quickly it would be broken down again due to radiation. The study concluded with the exciting result that the current data evaluation by the colleagues is not in vain, because theoretically it's possible that biogenic sulfur gases on hydrogen-rich ocean worlds like K2-18b could accumulate to detectable concentrations. And yet, as so often, the big but follows at this point, because this only applies if the organisms of K2-18b are real workhorses. In fact, the extraterrestrial DMS production would have to exceed that on Earth by a factor of 20 for us to be able to register it with our instruments. This is for the simple reason that most of the DMS is broken down again immediately by photochemical decomposition due to solar radiation. In the case of significantly higher concentrations, which are quite conceivable for hypothetical Hycean planets, a natural protective effect would, however, arise that would put a stop to the DMS loss. Accordingly, its degradation products, such as dimethyl sulfide and methanethiol, form a kind of protective shield around the lower atmospheric regions, which are thus protected from further DMS degradation. However, Only the future will tell to what extent this scenario corresponds to reality. What is already clear, however, is that the unequivocal confirmation of DMS would be no less than an unprecedented milestone in the history of space exploration. And while the team at Cambridge is currently busy evaluating the new datasets, as mentioned above, the lead scientist emphasizes that even one direct detection would be enough to revolutionize the entire history of science. No wonder, after all, humanity has been pondering for millennia whether there are other life forms out there, and ultimately, just a single example would be enough to end the millennia of speculation in one fell swoop. 2007 OR10 is a scientific miracle. Researchers would never have expected to discover another planet of this size so far out in our own solar system. Since its first sighting in 2007, this dwarf planet has attracted the attention of the scientific community. With a diameter of around 1,535 kilometers, it is one of the largest known dwarf planets in our solar system, and 2007 OR10 shows traces of a surface rich in complex organic compounds. This world was discovered by astronomers using the Samuel Oschin telescope at the Palomar Observatory. Its slow rotation of around 45 hours and its isolated location in the Kuiper Belt make it one of the most enigmatic objects we know. Now scientists want to use their new wonder weapon to get to the bottom of the planet. The James Webb Telescope is virtually predestined to analyze a distant and almost dark world like 2007 OR10 in great detail. James Webb misses nothing. Who would have thought that a single technical tool could revolutionize our entire world? Among experts, James Webb, the new space telescope, is already considered a legend. Yet the telescope is nothing more than a stroke of technical genius that we humans have constructed over decades of painstaking and ingenious work in order to finally unravel the last great mysteries of the universe. This most powerful telescope of all time has cost $11 billion, and we already know that this instrument is worth every single dollar. Since its launch in the summer of 2022, the telescope's first images are overturning everything we thought we knew. The Big Bang is under scrutiny. Our theories of the formation of matter and the evolution of galaxies were very likely wrong. We have to completely rethink the age and the finiteness or infinity of the universe. Webb showed us galaxies so old and so perfect that they could not possibly fit into a young universe. We saw images of black holes that were so huge and large at the dawn of time that they could not possibly exist according to our old astrophysics. We now have to rethink and open ourselves up to a completely new worldview. Planets like 2007 OR10 were already something of a warning to our science. We are far from knowing everything, and since the launch of Webb, we have had to realize more and more how little we really know about the universe. James Webb surpasses all previous telescopes with its outstanding technical capabilities. With its huge 6.5-meter primary mirror and state-of-the-art infrared instruments, Webb can look into the deepest and most distant regions of the universe. Its extraordinary sensitivity enables it to reliably detect light sources that are 13.5 billion years old, almost as old as the universe itself. Webb can see through dense dust clouds that block other telescopes, revealing hidden stars and planets. This ability to observe the universe in unprecedented detail makes the James Webb Telescope an invaluable tool for astronomy, opening doors every day to discoveries that will fundamentally change the way we think about the cosmos. What will Webb find on 2007 OR10? Imagine the JWST pointing its high-precision instruments at the mysterious dwarf planet 2007 OR10. With its advanced infrared sensors and spectroscopic instruments, Webb could analyze the composition of the surface of this distant celestial body in unprecedented detail. Using his near-infrared spectrograph and mid-infrared instrument, Webb would be able to identify the chemical fingerprints of the materials present on 2007 OR10. A possible spectrometer image could provide us with fascinating insights into which complex organic compounds are really present here and what story they will tell us. Researchers suspect that the unusual coloration of the planet is due to tholins. Traces of these compounds became visible through the interaction of ultraviolet light with methane and other simple organic molecules. Tholins are of particular interest for astrobiology, as they are considered to be building blocks for more complex organic molecules and would therefore be a basic building block for the development of life. Substances such as these have already been found in the vicinity of several moons in the solar system, which are also hot candidates for the first discovery of extraterrestrial life. Their presence on celestial bodies such as 2007 OR10 could indicate that the moons and dwarf planets played a previously unknown role in the origin of life in the solar system. These compounds could give us clues about how organic material forms and evolves in the outer solar system, and we gain important clues about the chemical and physical conditions in the early solar system. In addition, Webb could confirm the presence of water ice and other frozen substances that indicate the geological and climatic conditions on the dwarf planet. In addition to these incredible traces of life, 2007 OR10 has another secret concerning its very existence. The planet's orbit has not yet been fully confirmed, which is why it does not have a proper name and is only listed with a provisional catalog number. So far, the details of its exact orbit and physical properties are truly shrouded in mystery. 2007 OR10 is so far away from us that observation with previous telescopes was only possible under very difficult conditions. Webb could be of decisive help here. Through precise observations and long-term monitoring, the telescope could determine the planet's rotation period more accurately and precisely track its orbital movements in the Kuiper Belt. This data would be essential to calculate the orbit of this planet with greater accuracy, and once the criteria of the International Astronomical Union are met, the planet would finally get its own official name. Webb, on the trail of the mysterious rogue planets. Have you ever heard of rogue planets? These objects are free-roaming planets in space, and like 2007 OR10, they are extremely difficult to study. In the infinite vastness of interstellar space, the planets are downright tiny. But they do exist. This has been proven beyond doubt. Sometimes researchers succeed in detecting these planets, but as soon as they are captured, they elude observation again because they disappear into the vast darkness of the universe. The James Webb Telescope has the ability to detect and study even these elusive planets. Webb's sophisticated infrared instruments can detect even the low thermal intrinsic radiation of rogue planets. These planets have no light source of their own, and they move outside the luminosity of stars. Yet even these planets emit a minimal amount of radiation due to the processes within them and their movement through space, which we can detect using advanced instruments such as Webb's. This tremendous advance will allow scientists to analyze the properties and compositions of these free-floating planets for the first time and thus better understand the formation history of free-orbiting planets. Webb could help to determine the number and distribution of rogue planets in our galaxy. Researchers suspect a certain regularity to these phenomena. If we know how often and in which regions of the universe the phenomenon occurs, we will have added another piece of the puzzle to the overall picture of our cosmology. Thanks to Webb and his precise analyses, we could uncover the internal structure and even possible geological activity of even the smallest thermal emissions from 2007 OR10. Wandering planets showing signs of geologic processes and active cores would be another miracle of science. The universe has shown us time and time again, since we began exploring it, that impossible does not exist. Cool, ultra-hot Neptunes. We all know Neptune, the deep blue and rather cold ice giant at the outer edge of the solar system. But have you ever heard of ultra-hot Neptunes? Again, we have a fascinating, new, and truly unusual class of exoplanets that we would never have discovered without our immense advances in observational technology. These planets are similar to Neptune in composition, but orbit extremely close to their stars, often much closer than Mercury orbits our Sun. Because of this proximity, the surfaces of these Neptune-like planets reach incredibly high temperatures. At over 1700 degrees Celsius, these planets can be true horror worlds. These extreme conditions lead to many other interesting phenomena and turn existing theories about planet formation and evolution completely upside down. Ultra-hot Neptunes have such a hot surface that they can split gases such as hydrogen, helium, and methane into atomic components. These extreme temperatures can lead to atmospheric escape, where the planets lose their gases due to the intense radiation and strong stellar winds. A notable example of an ultra-hot Neptune is Kelt 9b, whose temperature is so high that molecules such as water cannot exist in a stable form, and instead break down into atomic hydrogen. The existence of ultra-hot Neptunes turns our old theories of planet formation upside down, because according to our conventional theories, such planets should not exist. They would have to be destroyed during their formation or by their extreme proximity to their stars. Their observation therefore challenges our understanding and forces scientists to develop new models and theories. These planets offer a unique opportunity to study the mechanisms of planetary migration and atmospheric escape under extreme conditions. The James Webb Telescope is now playing a crucial role in the study of ultra-hot Neptunes. With its sophisticated infrared instruments, Webb can also analyze in detail the thermal radiation and spectral signatures of these planets. Webb can examine the composition of the atmospheres and determine which molecules are actually present or absent in the environment of ultra-hot Neptunes. This data is crucial to understanding the chemical processes that take place under such extreme conditions. Using infrared spectroscopy, Webb easily penetrates the atmospheres of these planets and identifies the specific chemical fingerprints. This allows scientists to map the distribution of elements and molecules and study the effects of intense stellar radiation. Through long-form observations, Webb can not only monitor the atmospheric losses of these planets in detail, but also better understand the mechanisms of planetary migration. If we know more about the rate and extent of atmospheric loss, we can understand how these planets got so close to their stars and what processes keep them there. This helps scientists to improve their models of planet formation and evolution, and we gain more insight into the diverse workings of physical and chemical forces in the universe. Scientists have suspected, not just since Webb's launch, that there are other, previously undiscovered forces in the universe that could be important keys to understanding the big picture. Every strange and unexplained discovery gives us a clue to these forces, and with the JWST, we have the ultimate secret weapon to unravel these mysteries. Did exoplanets form around Fomalhaut? NASA named the mysterious-looking image of Fomalhaut in its dust shell, dusty debris. And who would have thought that this image would once again become the center of heated debate among scientists? Fomalhaut is a relatively young star located about 25 light-years from Earth in the constellation of the Southern Fish. It's one of the brightest stars in the night sky and was often regarded by the Persians as one of the 4 royal stars. Researchers often refer to the bright disk of dust and debris as Fomalhaut's belt. This disk is considered by scientists to be a potential planet-forming region, which is precisely why the JWST has now turned its keen eyes to this region. The JWST was not only built to show us the first epochs and oldest galaxies in the universe, but also to significantly improve our knowledge of exoplanets. Webb's infrared spectrometer effortlessly penetrates even the densest clusters of dust and gas, and thanks to this fantastic new technology, astronomers can now for the first time look through mysterious glass and analyze all supposed objects and suspicious clusters in detail. Are there really signs of planets here? Or is this disk really something else entirely? Strictly speaking, these are several disks made up of gas, dust particles, and the remains of collisions between smaller bodies. In disks like these that surround young stars, planets can form, or there are already fully formed planets that have so far eluded our eyes. In 2008, the discovery of Fomalhaut b, a potential exoplanet within the disk, was postulated. However, a short time later, the picture changed, and since then, researchers have been unsure whether and how many planets orbit the star. The precise spectrometer examination of the dust and debris disk around Fomalhaut can not only provide scientists with exact indications of ready-made planets or early stages of development, but also give them further insight into the composition of the materials surrounding the star. These unique analyses of the young star system provide us with valuable clues about the processes involved in the formation of stars and the subsequent evolution of a young star system. Thanks to its advanced instruments and its ability to observe in the infrared range, the JWST detects the thermal emission of the disks around Fomalhaut and provides astronomers with analyses of the data. Each individual light frequency provides more knowledge of the size, shape, composition, and other physical properties of the dust particles within the disk. Gases become visible and analyzable, slowly piecing together the picture of what is really going on in the disk around Fomalhaut. Previous sightings have already revealed several ring-shaped structures and gaps that could indicate the presence of exoplanets. The Great Dust Cloud is a huge dust cloud located in the dust disk of Fomalhaut. Previously, this dust cloud was thought to be the result of a collision between large objects in the disk, leading to the formation of large amounts of dust. Now, a picture is emerging that the condensations, which have been given the provisional names F2300c and F2550w, could be much more, namely evidence of young planets. If these initial estimates prove to be true in the coming weeks and months, this discovery would be a sensation, because then we will see some of the youngest exoplanets we have ever seen in the rings around Fomalhaut. Spotting exoplanets in the vastness of space is already very difficult. Making young planets visible was long considered impossible. Now that we can witness the birth and development of planets in other systems, we have a unique opportunity to understand the evolution of our own solar system in a completely new way. Formal skin, the mouth of the fish. Fomalhaut is a young star that has an old history here on Earth. Young in the cosmic context is 440 million years. 25 light-years away from us, the star of spectral class A3V shines in such a bright white-bluish color that Fomalhaut is one of the best-known stars on Earth. With a mass 1.92 times that of the Sun and 16 times the luminosity, Fomalhaut is definitely one of the brightest stars in the night sky. In ancient times, Fomalhaut was recognized by the Greeks as part of the constellation Piscis Austrinus, which to this day represents the southern fish. The name Fomalhaut comes from Arabic. It is a shortening of the term Fum al-Hut, which translates as mouth of the fish. The ancient Persians called it Hastarang, one of the 4 royal stars that were regarded as guardians of the heavens. In Islamic astronomy, Fomalhaut was described as part of the constellation Al-Dulf, the dolphin, and had a very special significance in mystical astrological practices. The Arabic names for stars have their origins in medieval Arabic astronomy, which already knew countless stars, gave them names, and even kept catalogs of them. The Arabs' knowledge of the stars was one of the most extensive ancient astronomical collections. Many of the old Arabic names were later adopted by European astronomers and are still in use today. Formal skin is also special to indigenous cultures. In the legends of some indigenous peoples of Australia, the brightly shining star was seen as a kind of messenger of light. The Aborigines called it the hearth, and it played a central role in stories about creation and the connection to the ancestors. These cultural interpretations and stories show the importance that formal skin has had in our human culture for thousands of years. The ancient Persians would probably never have dreamed of observing and studying the distant star in the way we can today, thanks to instruments such as the James Webb Space Telescope. Fomalhaut B, exoplanet or phantom? It's an exciting question whether and how many planets exist in the vicinity of Fomalhaut. Although the star is young, exoplanets should already be in development if there are any. The planets in our solar system also developed directly after our Sun from the remaining accumulations of dust and gas. Formal skin has been studied intensively since the 1980s with telescopes that were becoming increasingly better at the time. In 2004, observations by the Hubble Space Telescope revealed that the dust disk has a sharp inner boundary. It was then assumed for the first time that a massive object exerts a gravitational influence on the dust disk. The fact that the dust disk is elliptical was seen as a further indication of a possible planet. Researchers from the University of California had already expressed a similar suspicion in 2001. However, the evidence was lacking. In November 2008, a paper was published for the first time that postulated the possible existence of exoplanets in the Fomalhaut system and also presented good optical evidence for these planets. In 2010, Hubble turned his eyes to Fomalhaut once again. In the new images, however, there were indications that the inclined position of the disk could also be explained in another way. The evidence for the existence of the exoplanet Fomalhaut B was thus refuted. Despite the lack of evidence, speculation continued in some circles about the possible nature of Fomalhaut B and that it could be an Earth-like planet. The possible physical properties of Fomalhaut B could only be deduced by hypothetical orbital parameters, which in plain language meant that all conjectures were highly speculative. The calculations showed that, if it is a planet, it could be about half or twice the size of Jupiter. The size and the calculated surface temperature of -200 degrees Celsius alone argue against an Earth-like planet. Rather, it appears to be a gas planet. Fomalhaut B could be a kind of prevented sun similar to our Jupiter. Jupiter probably formed as one of the first planets in the system. If it had had a little more mass, it would have been dense enough to become a star. Then, we would have a binary solar system with 2 stars today. But in the Fomalhaut system, the tide turned once again, and later observations could not even prove that the planet Fomalhaut B really existed. New data could no longer prove the definite mass observed at the beginning of the 2000s, which led to the assumption that Fomalhaut B could rather be a short-lived dust cloud formed by the collision of 2 smaller objects. The JWST's infrared detectors were also unable to detect any significant infrared emissions that would indicate the presence of a planet. Planets should be visible through their own heat or reflected starlight in the infrared range, but despite a thorough search, no such evidence was found. Scientists currently believe that the object, which was mistaken for the exoplanet Fomalhaut B, is in fact not a solid planetary mass, but an object that has a dynamic structure that dissolves or changes over time. Click subscribe now and be part of every new video.